Now that we have a firm grasp of the second law of thermodynamics, we can take some of the relationships we discussed and use those to develop additional thermodynamic relationships that will be important to calculations that we do later in the semester. We start with what we will call the fundamental equation of thermodynamics, where we start with the first law equation for du, relating it to dq and dw. And then we start thinking about a reversible situation. Now, we know from the definition of entropy that ds is equal to dq reversible over t. So just a simple rearrangement gives us an expression for dq. And we also have an expression for dw for the reversible process, where the pressure here is the system pressure, not the external pressure, because in the reversible process the system pressure is infinitesimally close to the external pressure. Then we just simply make the substitution for dq and dw to get the fundamental equation du is equal to TdS minus PdV. It is important to note that we made the assumption here that work was PV work only. We did not include in this derivation other sources of work. Now, what about an irreversible situation? Does this equation apply? Well, the answer is yes, because if we take a look at all the variables in the fundamental equation, U, T, S, P, and V, these are all functions of state and therefore independent of path. So despite the fact that we used a reversible process to make this derivation, we can apply this equation to irreversible processes as well. The natural question would be why, because clearly in the irreversible case TdS is not equal to dq and negative PdV is not equal to dW, so how can this equation work? Well, even though they're not equal, it turns out that dW is greater than negative PdV and dq is less than TdS, so that means they exactly compensate for each other in a way that allows us to apply this equation. Okay, so now we're going to move on to applications of the Clausius inequality, which is based on the second law of thermodynamics. This is something we derived in an earlier video. And again, it's important to note that the central derivation of this law came from the second law, which said that delta S for the universe must be greater than or equal to 0. So anything that we derive with this expression is in fact an application of the second law of thermodynamics, and embedded in it will be the assumption that delta S for the universe must be greater than or equal to 0. Alright, so we have this expression TdS must be greater than or equal to dq for this, and again dq in this Clausius inequality is dq as process actually occurs. Remember that if it's a reversible process, then TdS will be equal to dq, but if it's an irreversible process, TdS will be greater than dq. Again, that comes from the second law of thermodynamics and applications of both the system and the surroundings in the thermodynamic universe. Now, of course, we know that from the first law, dq is equal to du minus dw, just a simple rearrangement. And if we take du and move it over to the left side of the equation, we simply have this expression here, just a little bit of algebraic manipulation. And now if we actually change the signs on all the terms here, we'll note that the equation becomes, the inequality becomes, changes from the greater than or equal to the less than or equal to expression. It's important to note that. And again, if we then additionally add the terms negative SDT plus SDT, this is going to be, it may not be clear right now why we're doing this, but it's going to allow us to derive an additional expression. We're essentially adding 0. So we're just adding 0 to the left-hand side of the equation in the form of this minus SDT plus SDT. And then what we're going to do is going to, again, do a little bit of algebraic rearrangement, moving SDT to the right side of the expression. And we're going to combine the two negative terms here because negative TDS minus SDT is negative DTS. And so we now have simplified the expression a little bit so that on the left side we have du minus DTS. Okay. Now, for an isothermal situation, of course, on the right side of the equation, the dt is equal to 0. And so we're left with this, where we have also combined the du minus dts terms into one differential. So we have the inequality du minus ts is less than or equal to dw. And then if we place the further constraint that the process be isochoric, which of course means that there's no volume change, and if we only assume PV work, all right, remember here we're only assuming PV work, only expansion work, we're not going to assume any other type of work, that will come later, then we have this result that du minus ts is less than or equal to 0. Now again, remember, we started with the Clausius inequality here, and that means that embedded in this inequality is the second law of thermodynamics. This is a condition for the second law for an isothermal process that's also isochoric, where only PV work is done. Any process that occurs that's isothermal and isochoric is going to have this particular condition. This is just a re-expression of the second law. This is equivalent. Again, I cannot emphasize this enough. This is equivalent to saying that for this type of process that's isothermal and isochoric, that delta S for the universe is greater than or equal to 0. And again, it would be equal in the case of a reversible process. So because this is a key expression of the second law of thermodynamics for an isothermal isochoric system, we're going to define this U minus Ts as a new function, which is called the Helmholtz energy and given the symbol A. And that means that for an isothermal isochoric process which involves PV work only, that dA is less than or equal to 0. So how would we use this? Well, if we have an isothermal isochoric process and we want to know whether it's going to occur spontaneously according to the second law, we very simply calculate the change in the Helmholtz energy for that process. If we find that it's less than 0, we know the process will occur spontaneously. If it's equal to 0, we have an equilibrium. We have a reversible process. We will have an equilibrium. So we use a Helmholtz energy to determine the spontaneity of a process anytime we have an isothermal isochoric system. Now, what else does it mean here? What's important to note is that, as we just said, this is less than or equal to 0 when we consider only PV work, but if there are other types of work involved in this, then what we're going to find is that dA is less than or equal to dW total. For a reversible process, it's equal to dW total. So if we have an isothermal reversible process, then dA is going to be equal to dW total for that particular process. Okay, it's going to be less than dW total. If it's an irreversible process, it's going to be equal to dW total for the reversible process. So if we have a reversible process, then if we calculate delta A for that process when it's isothermal, then that means we'll have an indicator of the total amount of work that we can get from that reversible process. And since we know that for the system, the negative W is equal to the work that the system performs. Remember, when work is negative, the system is doing work. That also means that delta A represents the maximum work we can get from the system. Let me repeat that. Negative delta A is equal to the maximum work we can get from the system. So this Helmholtz energy serves two functions. One, if we calculate delta A for an isochoric constant volume, is what isochoric represents, for an isochoric isothermal system, and we find that delta A is less than or equal to 0, that means as long as there is only PV work, that the process will be spontaneous. So the determination, again, of the sign of delta A determines whether a process will be spontaneous under isothermal isochoric conditions. In addition, delta A allows us to calculate the maximum amount of work that we can expect to get from the system, and that would be for a reversible process. So delta A allows us to calculate the maximum amount of work we can expect to get from the system for an isothermal process. So we have two things here. We get the maximum work from an isothermal process. We get the spontaneity for an isothermal isochoric process. We'll stop our discussion here with the Helmholtz function. In the next video, we'll talk about the Gibbs energy.